Hello, we are going to do the elementary reactions versus mechanisms. So the elementary reactions are less atoms, less bonds, simple, one step. The mechanisms are more atoms, that means more bonds, and they are complex and they are multi-steps. So that's the fundamental difference between the elementary and mechanisms, right? So elementary ones are something like carbon plus oxygen, just squeeze in and you get CO, carbon monoxide. But mechanism, one example is carbon, oxygen, hydrogen makes water and CO2. And then these two with the sunlight will make C6H12O6, which is glucose. It's a 10 steps or more depending on the pathway, right? So also we want to pay attention here the potential energy diagrams for elementary versus mechanisms. Elementary is a simple hump, one step, reactants and products, right? And in a multi-step, of course, few bumps, right? Reactants and products in the each ends. Now what's the difference? This one. This is called the transition state. I call the monster on the hilltop. Transition state cannot be touched, cannot be do anything with it. It's hypothetical. The monster is hypothetical, right? Here, these intermediates are in the living in the valley. They are real. They live in a valley in a way, right? They're real, can be done a lot of experiments with them. So intermediates are real. But this one also has transition state. We don't pay much attention in that. So depending on the complex reactions, right? Multi-step reactions. Now we also want to do another thing about playing with the multi-step reaction formulas. So let's take this one, 2NO2, F2 gives you 2NO2F. And this one is an overall reaction, but it is actually happening. Fluorine react with NO2 and gives you this F plus NO2. Okay, now then again, this what is left over? Yeah, this perhaps it's good to write FNO2, so it's easy for you to see. So F and NO2 again going to give you FNO2. Right, so these are two steps. I already wrote it for that. Right, now you can also say fluorine is a radical, and this radical and also this radical are intermediates. They can be cancelled out. These are the ones I was talking about living in the valley. Right, now left and right side should be balanced. Make sure you can handle left and right balanced way. So if you have to fill the blanks, right? So step 1 and step 2, the last addition together, adding together will give you overall reaction. In this case, collect all the left, F2 and 2NO2, and collect all the right, 2FNO2. That's the overall reaction. Check the balance left to the right, voila. Now, we also want to pay attention. The first step in this case is a slow reaction. Why it's a the second step is a fast reaction. So the fast reaction slows reaction because it's all neutral reactants. They are much slower to react. The fast reaction, why there is a radical involved in the beginning, that's why. The other thing you want to see, these steps to reactions are like math formula. It's a little bit of algebra. See, 4 and 10 is given, middle should be 6, right? And then let's say 4 and 6 is given, what is blank is 2. That's how you want to think. So don't get lost in the so fancy chemistry formula. Just think like they are math equations. It's easier. Now the slow step is in a reaction is we call the bottleneck. That's also the rate determining step. That's why it is slow. If you going in a journey, the slow area is the one making your destination at what time you can reach, right? So that's why this step, the highest activation energy, the highest mountain makes the decision that when you can reach there. So highest EA activation energy is in the rate determining step. So visually you can see and logically you can think why it is, right? Okay. Now we can move on to a bit different things. So we are a little bit okay to compare those two. Now you also want to pay attention to the kinetic molecular theory. That's the KMT. So in my previous video there's a little bit more details on it. So KMT tells you about how many particles, what's the kinetic energy, what's the temperature. Now we also know the rate of a reaction is directly proportional to the concentration, so we can multiply with the K, the rate constant. That's actually telling you something about the temperature, something about the energy, kinetic energy. That's why the importance, right? So the K never change without changing the temperature, right? So let's compare some other things here. Let's say so zero types of different types of reactions. So the zeroth order, first order, second order, third order, and so on, we can say, right? In the zeroth order, A goes to P, and then in the first order, A goes to P again. But in the zeroth order, the value or the power is 0. In the first order, power is 1. In the second order, power is 2. A to B or A squared, either way. Third one also again, third molecular reactions, ABC goes to product, and ABC 1 1 1, it's the third order. Or you can simply say 3 times of A actually. That will give you the product. That's also Ka to the third power. That's the termolar, termolecular, or third order. So that's how you separate them: 0, first order, second order, third order, right? So the rates are different. And now we should know what's the differential and integral formulas and equations, how to handle that. In kinetic classes mostly you're going to see them. And let's take XYZ, some crazy 3 reactions, right? So the first one, you double the reactants, it doesn't change anything, 0 rate. Y, you double, it's double the rate. Third one, you double the concentration, it quadruples. Now first, second, third, Y and Z did not change anything, so therefore we need to find another way. What's another way? Instead of the molarity versus time, this one, ln reactant versus time, and 1 over reactant versus time. So we don't have to do that one. This is done 200 years ago, right? So that's not the fundamental difference. So now we can label them 0th, first and second order, because 0th order did not change the rate with doubling the concentration. First order, double the concentration, double the rate, and second order, double the concentration, quadruple the rate, right? Now these are the things side by side with the graphs you want to compare. So the rate law is K to the R0, and first order K to the R first, and second order K to the R squared, right? So that's the rate law. Now what's the integrated formula is also important. So this one with the time, right? A is minus KT, T for the time, to the A naught. A naught is the initial concentration. And first order is ln A equals to minus KT ln A naught, right? So then the second order, 1 to the 1 over A, KT 1 over A naught. So that's what the time involvement in an integrated formula. This also can be written as y is minus mx plus c, and the last one is y is minus mx without the minus, right? The graphs should look like these 3. The previously I drew that one, right? So compare the 3 together like this way. It's easier to see the difference between the 3 and why the y-axis are different for each, right? The other thing is half-life. So the half-life also different for all 3. So first one, A naught over 2K. And second one, for the first order, is ln2 over K. ln2 is actually 0.693, and that's also you can put there. T half for the second order is 1 over K A naught. Now that just if you're given the half-life, or if you're given the K, how do you find out the time, or K, right? So the units also sometimes important. Rate is K in the 0th order. So the rate is mole over second K, and the units of the K is that one. So you can also rewrite this on moles over per moles over molarity per second. For the first order, you can say K to the M here, and the rate is M over S. So M to M cancels out. K is actually 1 over S, K is S minus 1. That's an easy one for first order. Now second order, rate is M over S, K is M over S squared. So the MS cancels out to the squared MS. So that means K is S over M. So we can rewrite this one, M minus 1 and S, right? So that's how the units are. So these units are sometimes can be in multiple choice questions, right? Okay, there's another smaller portion that we should talk about. That's also AP and IB and some of the University First Year and PChem classes you will see this, right? And let's look at the Arrhenius equation and how we use it, right? So the Arrhenius equation is giving you the link between temperature and the nature of the reactants. So the K is AE minus EA activation energy over RT, right? So now this one can be multiplied by ln to get rid of the e to the power. So ln K, ln A minus EA over RT. That just ln just to get rid of the e. So therefore ln K, ln A comes back here, but you get rid of the e to the power, right? Now we can rearrange this one. So ln K is minus EAR 1 over T plus ln A just by algebraic methods, right? So this looks like y is mx plus c. Now everywhere I was talking about that because that's the linear graph with lines, not hyperbolic type. So we can do evaluations and calculations based on that. So you have a line like that, we can actually extrapolate and we can get the ln A. ln A is the nature of the reactants. So that's what the ln A. So we can calculate EA, the activation energy, using the slope. And also R is given normally 8.3145 joules over k mole. So that's how the R you can just copy from a data sheet, right? Now let's say two situations. Same reaction happens at 20 degrees, reactant going to product, or 30-degree reactant going to product. So the K1 and K2, like I said, that's the only thing going to be different. And then the T1 and T2 is different, therefore K1 and K2 different. Rest is almost the same. So we can plug in that Arrhenius derivative into this each situation. So ln K1 E minus EAR over R1 over T1 plus ln A, and for the second sample also the same way. Now we can do 2 minus 1, the difference between the two. You can write it algebraically. You can correct this one as ln K2 K over K1 equals to minus EAR. That's all the same for both. And 1 over T2 minus 1 over T1. Now this formula could be slightly different in different when the teachers are teaching it differently, but still this is a good way to look at it, right? And then you can solve K1 over K2 or T2 or T1 you can find, or even EA you can calculate, right? So thanks, and any questions, just drop a line there and my students will print and make it, send it to me, and then I'll answer. Thank you.